So first experiment I wanted to demonstrate using a built-in data set. The next exercise, let us work on our own data set. Okay. So already we have imported from Keras dataset import MNIST. So in Google, if you type for MNIST, it is a popular handwritten digit dataset. We have around 50,000 training images. In Google, just you type for MNIST digit dataset. These are all handwritten digits like this. Each digit, we have the variations around nearly 10,000 variations for each digits. Nearly around 10,000 variations. So let us load the data set and we'll see, okay, how many records are there in each digit. MNIST.load data. It's a built-in data set which is part of your Keras framework. I just check what is the shape of X string. So the moment you run that cell, okay, then you can check xtrain.shape. 60,000 images. Each image size is 28 by 28. They are training images. Similarly, you can check what is the shape of xtest shape. 10,000 test images are there. 60,000 training images and 10,000 test images are there. Okay, if you wanted to visually see a particular image, okay, how you can access in Python. Say, for example, the first image I wanted to see. What is the first image from xstring? It's a multi-dimensional array, right? It's a 3D array. To access the first image, you have to specify 0 index, comma, colon, comma, colon. When you say 0, comma, colon, comma, colon, you can see a 28 cross 28 matrix. This is a 28 cross 28 matrix. Okay, you can see 28 cross 28 matrix. But we wanted to see this as an image, right? So for that, you can make use of OpenCV package to display this as an image, or even matplotlib package. We can use it directly to see visualize this as an image. So how you can visualize this using plt.imshow function. Use the plt.imshow function. Randomly, you pick any one image and you can say, for example, I wanted to see the 0th index. What is the image? Because this PLT function imshow by default, it will try to give a false coloring, okay, color image. That is why you have to say it's a color map gray. It is a single channel image. Next exercise, I'll be working with the color image. Okay, we'll be working with color image. So the first character is digit 5. Second image after 5, we have got 0, isn't it? 0. Then index number 2. So 504, right? So let us quickly cross check what is the corresponding labels. The corresponding labels are stored. Insert a cell. Who is storing the label for these guys? Y train, right? Y train square bracket colon 3. First image is 5. The corresponding label is given in integer 5. But to the model, I have to present. I cannot pass as integer. We have to present as one hot encoded vector. Because there are 10 classes, right? Your output layer is going to be like a 10 neurons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose for the digit 5, whenever the digit 5 this pattern is being presented, your output target 0, 1, 2, 3, 4, 5. Okay, your fifth node 0, 1, 2, 3, 4, 5 will be assigned 100% probability. The other nodes are given 0% probability. This is called one hot encoding. This node will take 100% probability. The remaining node should take a 0. Whenever we are training the pattern 5, next pattern is 0, right? Whenever we are training the pattern 0, Okay, the first node should take 100% probability. The remaining node should take a 0% probability. So in Python, we have a package called np.utils package, which is going to convert all your integer labels into one-hot encoded labels. So this is the way your deep learning architecture will accept your output label. Just like integer label, it will not. But originally, the data is given in the form of an integer, but we have to convert this to one-hot encoding. Then only we have to present to the model. Okay. So we just quickly cross-checked. Similarly, if you wanted to see first 3 test images, okay, I wanted to see first 3 test images, 0th index, you just copy paste the same line. Okay, plt.im show, instead of xtrain, you are going to use xtest. What is the first test image? It is a 7 character. Then we have character 2. Then we have character 1. Okay, 7 to 1. Let us check the labels. Y test square bracket. Look at the 7 to 1. So the labels are intact. If you'd like to know how many labels are in each characters, okay, you can make use of this value counts. This value counts, it's going to tell us how many test records are there in each character. See, for example, for 0 alone, we have 980 characters for the test images, validation images. Character 1, we have 1135. Character 2, we have 1032 patterns. Digit 3, we have 1010 patterns. So put together all 10,000 records are there. Similarly, you can do the value counts for training data set also. So Y train. So the same line you can just copy paste. So look at that. Almost for each characters, we have around some 5,000 to 6,000 characters are there. Different orientations, different way the strokes, because different people write it in a different manner, right? The same, everybody will not write, say 4, one person will be writing like this, another person will be writing like this. 4. So there are different around for each characters. We have around, see, for example, 4, we have 5,842 different varieties of 4. Digit 1, 6,740. So digit each one put together all, we have 60,000 training images and 10,000 test images. So what we have done, we just loaded the data. Okay. Since it is the handwritten digits, isn't it? My pixel intensity is not important for, isn't it? I wanted to know if there is a pattern called 5 means. I don't want to, I'm not interested how exactly this 5 intensity it has taken, whether it's a gray level 156, 158, 158 for this stroke, and again for this stroke it is 158, 172, 180, and again for this stroke whether it's a 172, 170 or 170. Each and every intensity is not so important for me, because after all I wanted to get to know, okay, some of the edge informations. Okay, simply even I can represent this as a monochrome image. The entire background is black and my foreground pixel is white pixels. Okay, still my model can able to understand the edges, isn't it? If there are some medical images I'm working with, or some radar imagery I'm working with, or NDT images I'm working with, their texture informations are important. There I should keep my actual pixel intensities. But here, it is just being a character recognition task. It is just a very simple digits or alphabets. For these kind of orientation based features, even I can work with the binary images. A small data preparation part we are going to do. So what we are going to do, that is the reason first I printed the actual intensities and I've shown you the matrix value. I have shown the matrix value. Hope you have seen the matrix value. The two X train, I just printed X train square bracket 0, colon, colon. You have seen all these intensities are not botheration for. So what I'm going to do, first I'm going to threshold this. Okay, we are going to threshold this and make it as a uniform intensity, like a bright pixel and the dark background. So for this data preparation part, okay, so I'm going to make use of OpenCV package. So using OpenCV library, we are doing this thresholding. All the training images and all the test images, we threshold. So take the lines from the code share. So I'm executing these lines. The updated array is being kept in R1, R2. Okay, all my training images after thresholding, it's kept in R1 and R2 respectively. Test images are in R2. What is the threshold I am taking is all the intensity values are 100 and above will be treated as a bright pixel to 55, else it will be treated as a 0. Okay. So there are various formattings are there. Okay, let us not go into the detail of that. So sometimes we may get the negative of the thresholded image. Whether you wanted to keep the object pixel dark and the background bright. In that cases, I have to put INV. Okay, by changing these options. Okay, you can play around with your outputs. Inverse. These options are there. Okay, but here anyhow, I wanted to go with the standard option, binary thresholded pattern. I would like to cross check how that pattern looks like before and after thresholding. Okay. So let me take one sample image. So plt.im show xtrain index number 2. This is where the pattern 4, right? You can see the pattern 4 with the different intensity variations. Okay. Now after thresholding, your xtrain is being converted to R1, right? Now I'm going to use, let me copy paste this line and insert in the next cell. And in the place of xtrain, I'm going to use capital R1. The same index number 2. Look at this. After thresholding, it looks a pure white. Okay, so the pure white. All the detailed intensity information is not needed for. Similarly, you can check any other text. Say we'll check the first one. I think first is 5, right? 5. This is after processing. The pattern 5 is being represented like this. Okay. So this is the first step we are doing. All the not only the training image, test images also. Okay. So R1 and R2, right? Let us cross check the shape of R1 and R2. We didn't modify the shape and all. Okay, only we have done the thresholding part. Okay. Now this step is very crucial. We should prepare the data suitable for our framework. We are using a TensorFlow framework. So according to the TensorFlow framework, we are presenting the training and the validation record. That is the next step after thresholding. So let me explain what we do here. So your TensorFlow framework should be like this. Number of images, which is 60,000 training images. Okay, width into height into channel. Even it is a monochrome image, I should explicitly say it is a single channel. You should not leave it like this. This kind of shape it will not accept. TensorFlow will not accept. It will ask you how many channels it will ask. Even if it is a single channel, we have to explicitly say 60,000 28 by 28, comma 1. If it is a color image, I should say comma 3. Okay. And moreover, I have to typecast the data type as a floating point 30. So this is the requirement for the TensorFlow environment. So let us run this and I keep this x underscore train, x underscore test. Okay, I'm not going to overwrite on the earlier x train, earlier x test. Okay, just to see the difference. Your earlier x train, and x test shape was like this. Okay, now x underscore train, x underscore test shape, if you do, it says 10,000, 28, 28, comma 1 single channel. Okay, earlier it was saying only up to 28 by 28. Now additionally, the channel information also given. Also, I have commented here, you could see that for Theano backend, some people build an application with the Theano backend. In that case, channel first, whereas the TensorFlow channel last. So if you are preparing the data set for the Theano framework, the data preparation should go like this: 60,000 single channel 28, 28. This is for the Theano backend. But anyhow, Theano is not a popular framework. Let us not bother. Just to give an idea that how other frameworks are accepting the data in what format. Okay. So we have prepared this, isn't it? So we have prepared the data, and now this portion is very important: scaling. I don't want to keep the pixel 0 and 255. Rather, I would like to keep it as a 0 and 1. Okay. Sorry, the same thing I pasted it. Instead of keeping the pixel 0 and 255, we would like to keep it as a 0 and 1. So for that, this max scaling will do that process. So whenever there is a gray level, because now we have a gray level, 0 means background and object pixel is being represented as 255, right? Now I wanted to keep the object pixel as 1 and the background remains same. So we have got 0, 0, 0, 0, 0, 0. And okay, there is a pattern like the 1. Okay, 0, 0, 255, 0, 0, 255, 0, 0, 0, 0, 255. After this process, okay, wherever you have this 1, instead of 255, it converted to 1, 1, 1. Because 255 divided by 255 become 1. So 0 divided by 255 remains 0. So this is what the max scaling will do. So let me run this portion, max scaling. After this, okay, all the gray levels. If at all, if you are interested, I will show you x underscore train square bracket 0, comma, colon, comma, colon. You can see either 0 and 1 pixels will be there. So background will be 0 and the object pixels are closer to 1. And next important step is, I told you, one hot encoding. Your training labels and test labels should be converted to one hot encoded using the nputils package. nputils to categorical. White train, all the labels of training record is stored in white train in the integer format. Similarly, all the test record labels are in integer format in white test. So we are converting this to one hot encoding. Say for example, let me check one reference. Say for example, the first, what is the first label of your training record? Integer 5, right? After y underscore train, let me print the first index one. You can see 0th index 0, 1, 2, 3, 4 at 5, 100% probability. The fifth index, because the first label is 5, right? Suppose if you wanted to verify for, or maybe I'll verify for 9. If I wanted to verify for 9, 0, 1, 2, 3, 4, right? Fourth index. For 9, the last should be 1, 100%, remain all 0, right? 5, 6, 7, 8 is the ninth index. And this is the 0th index record, first record, second record, third record, fourth position of the image, which is the character 9. So let me check here at the fourth position, 0, 1, 2, 3, 4. Originally, if you ask who's at the fourth index, it is going to give you only the integer 9. Okay. Now in y underscore train, I'm going to ask you who's at the position 4. It is going to give me one hot encoded version. The last node is 100% probability, the remaining are zeros. Okay. So this is the core, your modeling. This is the core part of the model. Just for the comparison purpose, I have done another model, which is not a conventional version. Okay, I'll tell you that part little later on. Maybe tomorrow I'll tell you for what purpose I have taken another version of that model. So this is the main architecture. Okay, this is the heart of your model. From here, the core modeling happens. So in the Keras framework, the modeling is very simple, just like a building block. Okay. So we have to connect all the chain of models, chain of events. Okay, what should come first? What should come next? In the block diagram, we have seen, right, the end-to-end architecture. First, we started with the input image, then a convolution layer, followed by max pool, again another convolution layer, followed by max pool. According to your design, you have to keep on. So first, always your model, you have to specify sequential. This is by default. This is going to be the first line. Whatever the architecture you're going to design, you have to first declare. Left hand side, any name you can specify. Okay. Suppose some 2 or 3 different architecture you're going to design. Okay, one architecture with only one convolution layer, another architecture with the 2 convolution layer, one convolution layer with the 5 filter, another architecture with 7 filters. You wanted to make a comparative study and all. So for that purpose, you can name it as a model 1, model 2, model 3. Simultaneously, you can try multiple architecture and you compare the performance. So here I named this as a model 2 sequential. What is the first layer I'm adding? Model 2.add. I'm adding a 2-dimensional convolution, CONV 2D. What is the first entry here? The first entry, this is number of filters. We are using 4 filters. What is the size of the input image? 28 by 28, right? 28 by 28. It's a single channel. 4 filters we are using. What is the kernel size I'm using? Because the image size is very small, either you can go with the 3 by 3 kernel or 5 cross 5 kernel. Okay, beyond that is not recommended because the image size is very small. Suppose if your image size is something like 500 cross 500 and all, or even 1000 cross 1000, maybe you can try with 7 cross 7 or 11 cross 11 filter. But the image is very small, so you can play around between 3 by 3 and 5 cross. So here I use 5 cross 5. And this is very important. You have to tell what is the input shape is coming. What is the dimension? Your input images, input shape. So our input image is of 28 by 28 single channel. Number of images you don't need to specify. Automatically, it will by default understand none underscore 28, 28, 1. Sometimes you may train with 50,000 images. Sometimes you may train with 40,000 images. Should be independent of number of images you train. So that is why number of records you're going to train, no need to tell explicitly, but the dimension you should tell explicitly. And in the convolution layer, I told you ReLU activation function. So we are using a ReLU activation function. So that is the definition of convolution layer. So can you tell me what is the output size of the convolution layer? 28 minus 5 plus 1. 24 by 24. 4 filters. So into 4. And I'm using a max pool 2 by 2. So this is after max pooling, it becomes 12 by 12 into 4, isn't it? So max pool 2D, pool size 2 by 2. And then we flatten it. So 144 into 3 after flattening it. So this is going to be your input features. And from here onwards, your fully connected neural network. Can you tell me, by looking at these two lines, how many hidden layers I have used in the architecture? Can you tell me in the fully connected zone, how many hidden layers I have used? Very good. Only one hidden layer. Okay, we have used only one hidden layer. One hidden layer with the 32 neurons. Again, by experimentation only. Okay. So why 32 neurons? By experimentations. Why only one hidden layer? Again, by experimentations. And the last dense layer. So all your fully connected layer has to be defined as a dense. Okay, your layer name is called as a dense 32. This is my first hidden layer with the 32 neurons. First hidden layer with the 32 neuron. This is the output layer. Why 10 neuron? Because we have 10 class. Okay, all the layers you can use the relative activation function, but in the output layer, strictly, you have only two choices. Whenever you work with the binary class, whenever you have two class, okay, you can use sigmoid activation function. But more than two classes, we are using softmax. So now let us run. Now your model design, this is the blueprint. Okay, the moment you execute this, so there are two stages before you run this. One is the compilation and then training. So I need to compile this model. There are two steps. So compilation, it is going to build a framework, the backend for you to prepare the TensorFlow backend for you. Something like a blueprint. It's prepare the blueprint and keep the training process ready for your computation process. So we have to tell some three important parameters here. One is loss. Since it is a classification problem, I should pass the loss as a categorical underscore cross entropy. When you train the model for the two classes, instead of categorical, I should use binary BINA or a binary underscore cross entropy. And the optimizer, I told you there are two ways you can use. One is the default is stochastic gradient descent. But when working with a nonlinear model, okay, stochastic gradient descent will get trapped with local minima issues. So we use a adaptive moment gradient descent architecture learning process. So ADAM. So the differences I will tell you tomorrow. Okay. So what is the strategy that ADAM is going to do to avoid the local minima trap? And the metric is to display the accuracy every time during the compilation. I wanted to see the accuracy score. And look at this, how I fit my model, X train, Y train. I pass something called a batch size. Remember when we discussed the gradient descent concept, do you remember we calculate the total error gradient, sum of delta beta naught or summation of the delta W bias or summation of the delta W1. This is one way. This is called as a full batch training. That means once the entire record is being presented, entire training record is being presented, the total error gradient is being used to update the weights. That is not a good strategy because here we have 60,000 records. Once the entire 60,000 record is being presented one time, that is called as a one iteration or one epoch. Your model tends to underfit. So what we do, we present the record batch wise. So per batch, we have 200 record per batch. Okay, like a batch. Each batch, we are going to use 200 records. It's being randomly taken. So 60,000 divided by 200. So you have totally, we have got 300 bags like this. Totally, you have got 300 bags. Per bag, you have got 200 images. So instead of presenting entire 60,000 images exposed to the model, what we do, first 200 images, randomly I present 200 images. Whatever the error contributed by the 200 images, that we computed y minus y cap, hope you remember y minus y cap and then y cap into 1 minus y cap. For this calculation, I should do the calculation for these 200 images. I should take the total of that. For the 200 total, I should substitute. Then we call this process as a mini batch training. Otherwise, it is called as a full batch training. What the code you have seen in the toy example is a full batch training. Okay, but here we are doing is a mini batch training. Again, the choice of how many record per batch and all, it's all depend upon the size of your training records, and you can play around with this. Again, it is something you can play around between underfit and overfit. The idea, you can play around with this. It will take around 50 iterations only I'm giving, just for the quick convergence. Let us see how much time it takes. See, to make the process little speed up, you can go to runtime. Okay, change runtime. The hardware accelerator, I have not selected GPU, but anyhow, this exercise, it won't consume much time. But however, if you select here, you have an option to select GPU and you can run. It could be a bit quicker. Okay, anyhow, because the moment if I change now means it will modify from the beginning. All the cells I have to rerun from the beginning. See, this is the first epoch. Totally, I told you 300 bags, right? Each bag is size is 200 images. So the first epoch, once all 300 bags are being presented, completed one. So initially the loss is 0.58, the accuracy is 83%, training accuracy and validation accuracy is 90. Now the second epoch is working on. Second epoch, compared to the earlier epoch, it has tried to minimize the loss. For the first iteration, you can see the loss is 0.58. Minimize the loss. Can you see? From 0.5877, the loss is being reduced to 0.2099. This is the training accuracy, 93%, validation accuracy is 95%. And the third iteration is going on. It would take some time. In the meanwhile, once it executed, okay, once it executed, you can see the performance metric. So how to save the model and how to reload the model and these ideas and all is reserved for tomorrow discussion. I skip. There are certain, whichever the portion I'm skipping, don't worry, I'll be discussing tomorrow. So the core idea of the implementation of the CNN architecture alone we are focusing on. Okay, the other peripherals and all I reserved for tomorrow's discussion. Once you executed, okay, you have to do model.predict. Okay, and how your model is predicting for all the records, because the model.predict will return all the results in one hot encoded version, isn't it? Suppose if when you present any particular test record, say for example, what is the first record model has predicted? Our model will be predicting in one hot encoded version, 0, 0, 0.11, 0.15, like 0.21, 0015, like this probability scores, 0, 1, 2, 3. So this guy may take a higher probability. Say for example, this is 0.95. Rest all other nodes are taking a very less probability, closer to 0. What I need to do when I do argmax for this, argmax, the 7th node got the highest value, right? It is going to return that integer. So which index got the highest value? It is going to return the argmax is going to return the corresponding label value. If I simply say np.max of means, it is going to return the maximum probability value to return. but rather I'm asking for np.max, I'm asking for np.argmax, I'm asking. So argmax is going to return the position of that maximum probable value, is going to return. So that way, if I convert all the predicted value, the form of I run a for loop for all the predicted value, and I collect all the integer values, the predicted integer values are being appended in ypred variable. Okay, so initially my ypred will have all the one hot encoded version predicted, and I'm converting to the integer value, I'm converting back. So now I can call the matrix.confusion matrix y test, and with respect to the predicted value, you can see this is the confusion matrix. And another report I'm printing, classification report. See the total number of 0 whenever we presented 980 test record 0 characters, 980. Model has successfully predicted 973 records, successfully predicted. There were 7 records are being misclassified, isn't it? That means there is 1 0 wrongly predicted as 1. 2. 1 0 is wrongly predicted as 4. 1 0 is wrongly predicted as 5. 2 zeros are wrongly predicted as 6. 1 0 is wrongly predicted as 8. 1 0 is wrongly predicted as 9. These are the misclassifications. Likewise, how many ones model is testing? There were around 1135 ones. Out of 1135 ones, 1114 ones are correctly predicted. These are some of the misclassified records. So if I print something called precision recall matrix, you can see how each and every records have been predicted, what level of accuracy it is being predicted. But anyhow, let me rerun this cell. It was ran for the earlier case. Okay, let us see how many iteration is going on. Only the 50th iteration is going on. See, in this 50th iteration, you can see the loss keep on reducing. Can you see? 0.58, 0.20, 15, 12, 108, 0.094, 0.083, gradually decreasing, keep decreasing. At one point of time, you can see around 50th epoch almost gets saturated. We get 99% of accuracy in the training as well as the validation record. Here, training accuracy is 98 and the validation accuracy is almost 97.8. This is the 17th epoch which is going on. Okay, so let it run. In the meanwhile, I'll tell you how to understand this classification report. So there are two things. One is recall. Second metric is precision. The average of these two is called responsible. So for a good prediction model, both recall and the precision are equally important. So if I wanted to calculate what is the recall of digit 0, okay, out of total number of 0, how many total zeros we were validating? 980. Out of total 980, how many zeros are correctly predicted by the model? 973, right? So 973 out of 980. This is called recall score for digit 0. If you simplify this, you will get a score. Let us calculate this one. What is the score? 973 divided by 98. We got 99.28%. So the recall score for this is 99.28%. Then how can I calculate precision for digit 0? If I'm going to ask you, how many zeros are predicted by the model? Can you tell me? My question is, how many zeros are predicted by the model? Not only this 973, This 4 also model says 0, right? This one also model says 0. This one also model says 0. This 3 also model says 0. So I should add up all these guys along with 973. So let us add this 4, 5, 6, 9, 10, 18, 19, 25. So along with 973 plus 25, 998. Okay. So model totally, it is saying there were 998 zeros. Model predicts says that 0. But all 998s were not originally 0, isn't it? Really, how many are actually 0? 973 were actually 0. So how do I do the precision calculation? 973 out of total 998 predicted by the model. Let us work out this calculation. If I work out this calculation, this is 973 divided by 998. 97.49. This comes 97.49. Take the average of both. So 99.28 plus 97.49. I take an arithmetic mean, but the software package calculates the harmonic mean. Not a very big difference. It will come very closer value. Harmonic means 2 into precision into recall divided by precision plus recall. That is a harmonic mean. But arithmetic mean, I have done it. Not a very marginal difference only. So put together recall and precision, we got 98.39. Similarly, for the digit 1, for all the digits, it will print the classification report. What is the precision recall? So that is what I have printed here. So now it's 30th iteration. Can you see? Almost it reached 99.99. Training accuracy 99. Of course, the validation accuracy is 90, almost 98 it is. Look at the loss. 0.0269, 0.0231, 0.018. So have you understood the workflow, how you have to build an architecture and how you have to train and validate the performance? The other aspect of this, whatever I have mentioned in this code, I will be talking tomorrow to the context of tomorrow's discussion. Try to understand the core idea of the architecture, what you have to build. If you have to prepare your own data set, okay, you have to take some extra mechanism in data preparation part. So only that part is going to be unique, but your core idea is going to be the same. The core idea of the architecture, of course, according to that particular your specific image requirements, you can play around with the number of filters and the number of layers and all, but the idea, the building block of the architecture is almost same. The data preparation part alone is going to be unique. So you have received some link to download some malarial cell images. Okay, I will just tell you a couple of the data preparation part alone for 10 minutes, then we can wrap up for today. Just last 10 minutes. Okay, the complete architecture we'll be doing it tomorrow morning as the first exercise I'll show you. Then we'll move on to the next module, feedback architecture, after finishing this exercise. So what are the primary thing you should do is, first I have to set path. First, what you have to do, first you have to download all the images related to affected and infected cases. So first I try to tell in a very generic manner, so that not only for the specific case study. Say for example, you are going to build an application for some 4 classes. Okay, this first you have to prepare the images. You have to create 4 folders. class 1, class 2, class 3, class 4. First, say for example, I have got 150 images uploaded in this, 200 images, 180 images, some 220 images. So these are my training images. Each folder you have to upload first. If any pre-processing required for each images, respective, I have to create one empty folder for each class. Okay, C1 processed, C2 processed, C3 processed, C4 processed. One for each class, one folder. Already you uploaded in our malarial cell. What you have to do? You have to create two folders, one for affected, another for uninfected cases. Affected malarial cases, uninfected cases. Only two folders you are going to create. Whatever the link I have, you got the mail. You have received the mail about the instructions. The data file download. Use that link and download all the images. Okay, you will get all the affected cases. Upload one folder, and uninfected cases, there are two folders. Parallelly, what you need to create is affected processed, uninfected processed, two empty folders. Initially, they should be empty. This also should be empty. What we'll be doing it, I'll be using a for loop to read one after another images in this. Whatever the previous MNIST dataset, what are all the pre-processing we have done? We have thresholded the image. Okay, simple thresholding alone we did, right? Only thresholding. But these images, whereas the MNIST dataset images, all the images of uniform size 28 by 28. There is no requirement for resizing. But this malarial images, each and every images, whether empty folder is created into, no, not into that. Content, okay. Content drive, my drive. Okay, this is my Google Colab path. Up to this is common to everyone. You have created DL workshop. Okay, inside this, if I go inside the DL workshop, I should see one folder, affected folder, another folder, uninfected folder. Okay, and two more folder. Affected processed, uninfected processed. If I go inside DL workshop, I could see 1, 2, 3 folder. This is already filled with images. This also filled with images. This is empty. This is empty. I'm not creating this folder inside this. Okay. So inside DL workshop, I should see 1, 2, 3, 4 folders. 1, 2, 3, 4 folders. So in this case, I'm just doing, I'm resizing all the images to substandard size. Okay, standard rows into columns. Suppose your application demands color features, your color channels, you should keep the color image. Some applications, color information is not required for the texture details. In that case, you have to convert RGB to gray. So only there are some pre-processing may require a resize followed by RGB to gray conversions. Only this much. Some specific application after this, they may convert it to threshold and make it as a binary image. So the application to application, this data preparation part will change. What are all the pre-processing you do? For this malarial cell example, I'm not going to do any complicated pre-processing. Only one pre-processing I'm going to do. I'm going to read one by one image and I'm just resizing it, and I'm going to store the resized image in the processed folder. So that is the only one data preparation part. And the second part is the labeling. That is very crucial. So this first part alone you try to complete. Okay, I'm just sharing the instructions. So the same libraries, anyhow, you can work with whatever the libraries I have shared with you. You can work on the same set of libraries. because it's a one-time process. Okay, it's a one-time process. Tomorrow you no need to rerun this portion again, because once the folders, these empty folders are being filled, okay, you don't need to rerun this process again, because it will, because it's going to read certain images. At least each folder is going to work some 10 to 12 minutes, so that at least 20 minutes you can save tomorrow in the live session. So the first step is you have to specify which path you have kept all these things. So let me refresh the code share. Okay, so I have defined 4 paths. See, now finally this 50 epochs is over. Look at this: training accuracy 99.71 and the validation accuracy is 98.0. So it's a really good performance. After this 50 epochs, okay, I have to do model.predict. See here, this place I'm doing model.predict. What is our model name? Model 2, right? Model 2.predict. That result is being stored in yprint. Okay, whatever the number of test records, it has done the prediction. Model 2.predict X test. If you wanted to check ypredict, how many test records we have? 10,000, right? Can you see each prediction is of the dimension 10, 1 hot encoder. Suppose I wanted to check what is the shape of the first predicted value. Look at the probability scores. 1 hot, this is almost 0 into 10 to the power 15 minus 15 minus 10, almost 0, which is the highest probability. This node is the highest probability, isn't it? 0.99, highest probability. All other nodes are almost 0 into 10 to the power minus 13. Which index is this? 0, 1, 2, 3, 4, 5, 6, 7th index. When I do np.argmax of ypredict 0, it is returning 7th. Similarly, I check for the second position, second record, what is the prediction? Which node got the highest probability now? This node, right? 0, 1, 2, 0.99. 0, 1, 2, the character digit 2. I should get 2. So likewise, I do this for all the records in a loop so that I can construct a confusion matrix. Okay. So what are the 2 steps you have to do once after finishing the training process? Okay. So, okay, before you do this exercise, the last 2 steps, you do the prediction followed by converting all the labels to integer, and you are printing the confusion matrix. Here I have to print the confusion matrix, followed by classification report. It's a classification. It's a classification report. So the 2 step, the last 2 steps. So you can see the overall F1 score is 98, pretty decent. And the lowest score is for the digit 8 and 9, right? Where the difficult digits for the model. The easiest for the model is, see, digit 1 with 99%, and digit 4, 99%. The remaining are 98, and the difficult was digit 8 and 9 were the difficult ones. So the overall average is 98. Okay, we do more investigation on this result. Tomorrow also I'll be giving some insight about this, how to save the best model. And every time you don't need to reload, rerun the program every time. Okay. So when you run it, while during the running itself, you can save the best model and you can load it as a .h5 files. Next time you can directly load that .h5 files and you can load the trained weights directly. So how to do that process, I'll be telling you tomorrow. Now you have to prepare these two folders. You have to prepare first for the data set I have shared with you. One for loop you have to run. This is one for loop you have to run and prepare all the images to standard dimension 100 by 100 dimension. So I'm defining rows and columns. Look at this for loop, what we do in this for loop. For file in files, first it is opening the path 1. Path 1, we know what is in path 1. All the affected cases, right? All the affected cases. For file in files, files is already, it's referring to os.list directory path 1. That means my files, all the files, whatever I have uploaded in the path 1, the affected case, my files will be having the file name. Say for example, randomly one of the file I printed, this is the file name. C39P4. Okay, so like a PNG file. So the files will store all the file name. When you do for file in files, first it is accessing the first file. Appending to the path 1, it will append and it will access the first file. It's opening the first file and then it resizes according to the dimension what it knows. So, since here I'm going to process all the images in the color version, I'm not converting to the grayscale conversion. Otherwise, you can uncomment this. This line will convert all the color image to grayscale. IMG convert with the keyword capital L will convert all the image to the grayscale. And finally, I save the processed image in the path 3. Whatever the file format, original image was the same file format, I'm saving the file, all the PNG file format in the path 3. As soon as you run this loop, okay, your first empty folder will be filled. So before you run the second loop, make sure that os.list directory should be updated according to this time you are going to process uninfected cases, right? Path 2. So this time your files equivalent to os.list directory path 2 that you have to run it separately in another cell before you run the second loop. This line, you have to run this line separately. Then only it will access your second folder. After running this loop, you have to run this update os.list directory path 2. And then you run the same for loop. This time you are going to access from the path 2 and all the processed image you are going to save in path 4. Now your second empty folder also, as soon as you run these two lines, these two cells, your second empty folder also will be filled. Only this much portion you just try to complete with the 2 folder links are already shared with you. Just go through that link, try to download all the files and try to do these 2 steps. If you find any difficulty in these 2 steps, feel free to ask me tomorrow. Tomorrow also I will be demonstrating lively in front of you. We'll see how we prepare this. Once we prepare this, almost 50% of the job done. Remaining 50%, how you are going to do the labeling part. Once you have done the labeling part, then you can shuffle the full records. Till the time you do the labeling part, you are not supposed to shuffle all the class records. We have to keep the individual classes in the individual respective folders. Till the time you have to create the label. Once you create the label, I can pull all the training images in single folder. I can shuffle the records because I don't need to worry in shuffling because it will be shuffled along with the labels, so that I know which record is going where, which record along with the label in hand. Till the time you create the labels, okay, we should very careful in handling the each class. We should keep track of which class is being saved in which folder. So that portion is very crucial. Once we have done that, the remaining part is what the model building is same as like the previous thing. So let us discuss the architecture, how to build the model for this. So maybe 15 minutes, tomorrow 10-15 minutes, we can complete this task. Then I will show you one more case study. This is the example. You can start something from the scratch, isn't it? Start something from the scratch. We build the model from the scratch. But not always you need to build something from the scratch. You can also do some pre-trained models. You can load a pre-trained model and you can solve your own specific problem. How to do that? So that also I'll give one demonstration to understand how to make use of a pre-trained model and how to do the custom training. No need to train the full architecture. Only there are certain portion alone. If you do a little bit of fine tuning, if you do, that is more than enough. The earlier popular models, which is being trained on some popular data set, will be working for your own data set also. But the only thing is how you are going to use the pre-trained model and how intelligently you are going to use the pre-trained model. That technique also you will be learning that. So put together all these things will occupy 30-35 minutes. Then we can wrap up this. Then I will take you to a different architecture. What is feedback architecture? How this feedback architectures are very popular in the sequence forecasting problems, mainly for the NLP applications. Okay, word sequence forecasting and other applications, interesting applications to NLP. Okay, so that will be the agenda of tomorrow forenoon discussion. So before that, please try to complete these two tasks, whatever I have given to you. So there are 4 folders. Initially, you fill these 2 folders with images. You should keep these 2 as an empty folder. After running the 2 for loop, these empty folders should be filled with the processed images. Okay, so that is a homework task. Try to complete this and keep it